In a video I made a couple of days ago, I talked about these odd functions that are sort of negatively symmetrical around the y-axis. So like any positive area here is cancelled out by any negative area here. So if you're integrating between two symmetrical bounds, the integral is always just zero because this positive area will cancel with this negative area. And likewise here, you've got these areas that just cancel because one's positive and one's negative. These are called odd functions. And I talked about how this was quite a useful thing to know. And likewise for even functions, which are perfectly symmetrical around the y-axis, the integral between two symmetrical negative bounds like this is just going to be two lots of the integral on one side, because of course the integral on both sides is the same. Now it occurs to me that I could have said much more about this, and I just thought I'd make a very quick video to help you out with this, because I think from what I said, it's very easy to get the impression that, okay, well, this is quite nice, but it only works in two very specific circumstances, right? It works if the function is perfectly odd. And by the way, odd functions, of course, have odd numbers in their x powers. So 1, 7, 3, and 1. And this only works if the function is properly odd and only has that. And if the integration that you're doing is between two symmetrical bounds like this. But that's not quite true. You can use these ideas to quicken up your integration regardless of whether you have those two conditions. So for example, let's look at this function here. This function is neither even or odd completely, because you've got odd powers here but an even one here. And so we can see when we graph it that it's neither symmetrical around the y-axis nor sort of negatively symmetrical, in the sense that these areas are not just going to cancel out. So it seems that if I integrate this between 2 and minus 2, say, that there's nothing that I can really do to speed up this integration, but there actually completely is. You can use another really nice aspect of integration, which is, and you basically would very rarely want to do this, but you're allowed to, you can break up an integration into as many different parts as you want. So you can break this x cubed into its own integral, you can break this minus 3x squared into its own integral, and this minus x into its own as well. And the reason this is super helpful is because this is now an odd function, because it just has an odd power here. So this integral is 0, and so is that integral. And this is an even a function, because it's just gone next to 2. So this integral is the same as us going from 0 to 2 twice, with a negative because I'm taking away the whole thing. And this is a super easy integral to agree to, right? This is x cubed. I've chosen a nice one to work out nicely. 2 cubed is 8, times 2 is 16. You just get negative 16. So you can play this trick even if you don't have a perfectly even or odd function by just splitting it until it is perfectly even and odd functions. So that's quite a nice trick to know and can save you quite a lot of time if you're having to do an integration like this sometimes. The other trick you can know is, what if you're integrating between not a symmetrical bound? So this is an odd function, right? X to the power 3, x to the power 1. But it is symmetrical in this kind of negative area way. But we're not integrating between a symmetrical bound, so we can't just say this is equal to 0 because we've got the extra number. These don't quite match. But again, just like you can break up an integral into its own parts here, you can break up the bounds of an integral. So I can say this integral is the same as integrating between minus 3 and 3, and then plussing the integral between 3 and 4. And think about why this makes complete sense that I'm allowed to do this. Like, this is the total area between minus 3 and 4, so minus 3 all the way to 4, which is over here somewhere. You can just do the integral from minus 3 to 3, and then add on the last bit from 3 to 4 separately, right? You can do that. But of course, this bit is 0, and I haven't really achieved anything here, except that when I substitute in a 3, me personally, I much prefer substituting positive numbers than negative. Particularly when I've got negatives in the expression itself. I'm much less likely to make a mistake with my negatives if that number isn't negative. So a nice little trick if you see an even odd function, an odd function like this, is that you can just turn that negative into a positive, because essentially just all of that would be 0, like I said. And I didn't bother to finish this question off, but you'd get something like that. Anyway, thank you for watching.